Hello, I am Phoebe Lewis, the supplemental instructor for Dr. Byron Quinn's Natural Science Biology 1 course at Langston University. I am composing a series of review videos for your final, so this review video is the first one and it covers chapters 1 and 2. Now chapter 1 only focused on two main things, the scientific method and levels of organizations of living things. Now first, the scientific method is composed of 5 main steps: observation, question, hypothesis, experiment, and conclusion. Now remember, you guys use the scientific method every day in life. For example, you make an observation that your car doesn't start. Next, you ask a question. Why doesn't my car start? Then you formulate a hypothesis. Now remember, your hypothesis must be testable. Examples of valid hypotheses are my car is out of gas. Or you could say my car battery is dead. Now, an example of a not valid hypothesis would be kicking the tires. Kicking the tires is not testable. At best, it's an experiment, but it is not a valid hypothesis. I'm going to be late to work. That may be a consequence of your car not starting, but remember, it is not a hypothesis. So that is also not valid. Then, of course, you would do your experiment. Now, your experiment for your hypothesis saying that your car is out of gas would be, of course, to put gas in your car. To test your hypothesis that your car battery is dead, well, you could give your car battery a jump. Both of these are experiments. Then your conclusion would be that either your car was or was not out of gas, or your car battery was or was not dead. If your conclusion proves your hypothesis wrong, you have to start all over again. But that, of course, is the scientific method. Remember, observation, ask a question, make a hypothesis, test it with the experiment, and then conclusion. Now let's move on to the levels of organization of living things. Remember that life and matter is composed into a series of complexity, from the least complex to the most complex. Now I made a silly mnemonic device or acronym that might help you remember the levels of complexity, but remember, you don't have to use this. This is just something that you may use if it helps you. It is Adam, at the bottom of the screen here. Adam made O'Neill call Tisha over Uvu. Peter called before. So, let's start off with the least complex, which of course is the atom. Alright, then when two or more atoms join together, you get a molecule. Then when you get multiple molecules, you get an organelle. You guys learned your organelles, your mitochondria, your ribosomes, your lysosomes, your nucleus. These are your organelles. And remember, those organelles come together and make cells. The cells come together and make tissues. The tissues come together and make organs. Your organs come together and make organisms. Your organisms come together and make populations. Your populations come together and make communities. And of course, your communities come together and make biospheres. And so that is what you need to know for your levels of organization. On your test, guys, don't get confused. Make sure you read the question. These aren't hard concepts, but make sure you read the question. See if they're asking for the most complex or the least complex, because that can change your answer right there. So that's just my little piece of advice for that. But now, wasn't that easy? Let's move on to chapter 2. Okay, chapter 2 talks about elements and compounds, the structure of the atom, chemical bonds, molecular shape, and solvents, solutes, and solutions. So let's start off first and talk about elements versus compounds. Remember, you guys learned elements are pure substances. Your gold, your silver, your titanium, hydrogen, carbon, nitrogen. Those are elements. Now, when you break the element up into its smaller part, you're going to get an atom. So right here in the picture, right here, you have gold. The smallest piece of gold looks like this. It's an atom. On the other hand, you have compounds. Compounds are composed of two or more atoms. Some common compounds are table salt, as depicted in this picture, or water. You guys know water, H2O. Now, the smallest part of the compound is actually called a molecule. And so the molecule is depicted right here in ACL. So remember, atoms are the smallest part of what? Elements. Good job. And molecules are the smallest part of what? Compounds. All right. So let's move on and focus on the atom. The atom has two main areas. It has a nucleus and it has an electron shell. Now, you find that you have three main subatomic particles: the proton, the neutron, and the electron. And each of these subatomic particles determine a particular characteristic about the atom. So I advise you to make a chart and organize and remember these concepts. This is what my chart would look like. So if you want to, you might want to go ahead and write that down. You have your subatomic particles, your protons, your neutrons, your electrons, the location that they're found. Is there a charge? Does it have mass? And what does it influence? So let's first talk about the protons. You know that the protons are found where? In the nucleus. You know that it has what charge? A positive charge. And it does have a mass. What does it influence? It influences the identity of the atom, and we'll speak about that later. The neutrons now, where is it found? The nucleus. Does it have a charge? No. Neutrons are neutral. They don't have charges. Does it have a mass? Yes. So what does it influence? It influences the isotopes. We'll talk about that later as well. And then the electrons, last but not least, are found where? In the outer shell. They have what charge? Negative. Do they have a mass? No. Electrons do not have a substantial mass. But what do they influence? It influences reactivity. So let's get into animations and explanations of what we're talking about. Remember, each element has a unique number of protons, and they're found on the periodic table of elements right here. Now, if a scientist looks underneath a microscope and they observe one proton, that substance is, without a question, hydrogen. Now, if a scientist observes 6 protons, without a question, that substance is carbon. Thus, the number of protons determines the identity or name of the element. Now, neutrons are the second subatomic particle that we'll speak about. Neutrons determine isotopes, and remember, an isotope is an atom of the same element that has a different atomic mass due to differing numbers of neutrons. Now, I'd like to direct you to the blue arrows right here. The blue arrows show that each of these atoms have one proton in it, and as we determined before, the number of protons determine the identity. So considering the fact that each of these atoms have one proton, without a question, they have to be hydrogen. What you notice, however, is they have different numbers of neutrons. This first one has 0 neutrons of hydrogen. The one that we are going to call deuterium, which is just a name for isotope of hydrogen, has 1 neutron. And then tritium, another isotope of hydrogen, has 2 neutrons. And so the number of neutrons, if you refer to back to your chart, neutrons do have mass, although they don't have charge. And so with the presence of the neutrons there, they're going to change the atomic mass of the whole atom. And so that is the significance of isotopes. Basically, they all have the same number of protons, but they have different atomic masses because they have different numbers of the neutrons. So let's see how we can determine how many neutrons a given element has. Okay, the periodic table tells you the number of protons, which is of course the atomic number, and the atomic mass. Tells you right here. Let's take helium for example. It is atomic number 2, so therefore it has 2 protons, and it has atomic mass of 4.003. So doing some simple mathematics, you can know that number of protons plus the number of neutrons equals the atomic mass. So let's just take helium for example. If you see, as I mentioned, it has 2 protons. We don't know the number of neutrons yet, but we do know that the atomic mass is 4.003. So if we do some simple algebra, subtract 2 from each side, you find that your number of neutrons equals 2.003, or about 2. So in this particular element of helium, in this case, it has 2 protons, 2 neutrons, and we know that it has 2 electrons because there's no charge on there. So if it said helium plus or helium negative, it wouldn't have that would change the number of electrons, but because it's just helium, the number of protons is going to be equal to the number of electrons. The last subatomic particle that we'll speak about are the electrons. If you look at your chart, you'll notice that the electrons influence the reactivity of the atom, and they're found in the outer shells. The outer shells act like rooms with a given capacity. The first shell can fit 2 electrons in it, and each shell after that can fit 8 electrons in it. Most elements want to have 8 electrons in their outermost or valence shell of electrons so that they can abide by the octet rule, which says that elements are the most stable when they have 8 electrons in its valence level. Hydrogen and helium are exceptions to this rule, as they can be stable with only 2 electrons in their valence level. Let's do an exercise and determine how many valence electrons sodium has. Sodium is atomic number 11 on the periodic table. So that means that it has 11 protons and 11 electrons. We know that 2 can fit in the first level, so if we take the total number of electrons, 11, and we subtract that by the 2 that will go in the first orbital, we'll find that we need 9 more electrons to account for. We know that 8 can fit in the next level, so 9 minus 8 equals 1 electron, which means that sodium has 1 electron in its outermost level, and that is depicted in this picture right here. Elements that have the 8 electrons or octet in their valence levels are extremely stable and relatively unreactive. This accounts for your noble gases and are depicted right here in this column.